So today we're going to be talking about probabilistic analysis. So in general, when we're talking about runtime, we always take the worst case. So for like big O, big omega, theta, and all that stuff, we're always working with the worst case scenario because that's just kind of the standard we use because, we don't care about, what if things are really good. We want to be as safe as possible, so we take the worst case. However, given any algorithm, we can have a best case scenario, we can have a worst case scenario, of course, and we can also have the so-called average case scenario, right? And by average case, I mean, what you would expect out of any given random input, what kind of behavior can you expect from that algorithm? So let's take insertion sort, which pretty well known. The best case of insertion sort is theta n, which is linear. This is because if your input is already sorted, then you just have to go over the list once and you don't need to swap at all. It's great, right? If you have, let's say, 1, 2, 4, 5, right? Your loop just goes through this 1, 2, 4, 5, goes through it once, and you're like, great, I don't need to swap anything. Your worst case is n squared. This is when your list is in reverse order. When it's in reverse order, you have to swap all of the items. That means you have to go through the loop twice, which is why you get n squared. Now, interestingly enough, the average case and the worst case are both n squared for insertion sort. So, if our input data has some sort of randomization or just some sort of information we can gain from the input, we can perform some analysis on the probability of that randomization, right? That is what we mean by probabilistic analysis. We're using the probability to perform some analysis on it. All right, so as mentioned, probabilistic analysis is just the average case running time, right? If your algorithm has some randomization, we can base our analysis of the probability on that randomization, right? So we use the probability in our problem analysis. So basically this means that we have to have some sort of randomization for this algorithm. Now, ostensibly you can perform probabilistic analysis on any algorithm, right? For example, something like matrix multiplication, right? We know matrix multiplication always is consistently the same because you always have to multiply each of the items. So the worst case and the average case are the same. So technically you can perform probabilistic analysis on anything, even like deterministic algorithms, right? Like algorithms for which there is no randomization, but it's pretty much useless. So basically what I'm trying to get at is, perform probabilistic analysis on algorithms that have some randomization. All right. So an example we have here is what I call the recruiting problem. Now the formal example for this is called the hiring problem, but this is my modification of it because I think it's hopefully somewhat more intuitive and also a little bit more fun. So here's the scenario. You're trying to find a disciple, right? You're this great martial arts master and you want to recruit a disciple. So let's say here are the disciple candidates. Now you're very busy, so you can only recruit one disciple. And on top of that, you can only have one disciple trial or exam per day, right? So let's say we have 3 candidates and we only want one of these guys and we can only, interview or trial one of them on each day. Now, you're a very strict martial arts master. You will immediately decide to accept or reject this disciple, and after they're rejected, there is no other chance for them to come back, right? It's just done in there. And if you think the disciple that is interviewing right now is better than your current disciple, you will expel or you will kick out your current disciple and you will accept that disciple as your actual, official, singular disciple, right? Because again, you're very busy, so you only have one disciple. So let's do a quick run through, right? Your candidates. Day 1, let's say you get this guy. And, at the start you have no disciple, so you just accept him. And then day 2, we get her, and you're like, I'm going to interview you. And turns out you like her better than your current disciple, so you kick this guy out, and here is your disciple now. On the last day, you interview the final disciple, and turns out you like this disciple better than your current disciple, so you expel her, and here is your final disciple. So the disciple registry or the village or something like that, they will send one disciple at a time for you to interview. So our pseudocode looks like this. So we'll start off with the counter equals to 0, right? Because we have no disciple at the beginning. And then we'll simply iterate and loop through all the disciples, interview the candidates, and if they're better, you swap them out. If they're worse, you just reject them on the spot. Pretty straightforward. Now, let's think about the cost of this algorithm. So let's say we have n candidates and we have n acceptances. What I mean by acceptances is how many times you accept a disciple, or you hire that person, so to speak. Right, so in the example we just went over, like that one scenario, we had 3 acceptances because we accept the first one, we go to the second one, we find out she's better, so we accept her, and then we go to the third one, we find out he's better, so we accept him, right? So we kind of swap them out 3 separate times. So the cost of this is just O of n times ci plus m times ch, where ci is the interview cost and ch is the hire or the acceptance cost. And we always assume that the hiring cost or the acceptance cost is more than the interview cost. Because think about it this way. First of all, in this assumption, we're just going to say that the interview does not cost that much resources or time or anything like that. But the onboarding process, or when you train up a disciple, it costs a lot of your time and your energy because you have to onboard this person, you have to train them, you have to spend time with them, like make them do like exercises and whatnot. So we're trying to avoid having unnecessary acceptances, right? We want to minimize the amount of people we accept that are basically useless because we're very busy, so we want to optimize our time. Now, what is the worst case? Well, the worst case is what we had in this example, right? We have to swap out 3 times and we hire all of them, but then we expel 2 of them. So the worst case, in this case, right, it's just O of ci n plus c h n, which is equal to O of c h n, considering this property is true. So our paradigm for this kind of algorithm is just to find the winner, right? We want to find the best disciple, and we'll just say the variable m is the number of times we change the so-called winner, the number of times we hire or recruit or accept a disciple. Now, importantly, we don't have control over the order in which we receive the candidates, right? We don't know anything about that. And, we just don't have control over, what order the village sends us people. But this is a problem because, based on so for probabilistic analysis, we need some information, we need some data about the actual inputs, right? So we need this information so that we can make some educated, intelligent assumptions so that we can perform the analysis. So what do? Well, if we don't know, we don't know if they're sorted by like strength, they're sorted by height, they're sorted by age, right? We don't know anything, or they could be completely random. Because we don't know that, what we can do is we can manually shuffle the disciples and ensure that we have a random order. So we're not just saying, hey, I just accept the village's order, right? Because interestingly, right, sometimes if they're in some sort of order like this, it actually really messes up your algorithm. So when we're doing, expected runtime or like the average case, we want to make sure that, it doesn't skew our algorithm in a super weird way. So what we want to do is we want to use a randomized algorithm. What this basically means is, exactly what it sounds like, right? We just want to randomize this algorithm. We want to randomly choose a candidate. So we consider an algorithm randomized if the behavior of the algorithm is determined by some random number generator. And okay, technically speaking, there is no perfect RNG, right? There is no perfect random number generator, because a lot of times how they actually work like behind the curtain is they'll take a seed, which is, oftentimes it's like the timestamp of whatever is going on right now. They'll take the timestamp and then they'll use that as a seed and then like generate a number based on that. So it's technically not perfect. So there have been like interesting cases of people like hacking gambling systems based on that. But, in terms of theory, we just want to take a random number, right? So the formal definition of that is just, the random function. It will return an integer r such that it's between a and b, right? You're arranged like this. And we have this many possible values. So this is basically just the amount of values we have within this range. And we're saying all of these are equally likely. This is very important. They're all equally likely. So back to the example, right? If we shuffle the candidates, of course one of them will be the best, right? Let's say it's this guy. This guy, is a crybaby. She is easily distracted, but this guy, look at him. He is very strong and courageous and determined, right? So we know this guy is the best. So we do have a preference, but when we shuffle them, we don't know where he'll end up. And that's actually a good thing because, again, we want a randomized input so that we don't accidentally skew our algorithm and get a really weird result. We want to be able to estimate what is the average or expected output or the runtime of this algorithm. Sorry, not output, it's the runtime. So to help us with this process, help us with the analysis, we have something called an indicator random variable. It's just a very easy way to convert probability to expectation. Now, the definition of it is basically just like this, right? You have your indicator random variable here, and if the event A happens, it's a 1. If the event A does not happen, it is a 0. Very important that this is a binary choice. You can't have a case where it's like, oh, I have higher, like I have this guy as my disciple, but also like her at the same time. Like that is not the case. This is completely binary. So, for event A, let this x of A is the variable. We want to have that equal to the indicator random variable. Then, E of x is equal to P r of A. E of x is the expected value, and P r of A is the probability. Now, if you just look at this specific case, right, it seems kind of lame because you're just like, all right, like E is equal to PR, like what is even the point? So in this case, it's very trivial, it's like the expectation is equal to probability, right? Like no duh. However, in more complicated scenarios, we don't have a singular probability, right? A lot of times we actually want to add up the probabilities. We want to combine them into, one expected value. So that's why later on, we'll find some examples in which it's not trivial like this. But yeah, this is just a definition of, we have some expected value which is equal to, your probability. Now let's prove that the lemma is true. So we have some event A, and we have A naught or A bar, which is the complement of A, which is just the event A is not true. So given the expected value, we can just substitute this in, and then we can break it down like so, right? 1 is the total. So we know 100% of the time event A will happen, plus 0% of the time not A will happen, right? This basically just means we know 100% of the time this event will happen, and 0% of the time this event will not happen. And therefore, we have proved that these two are equal. Again, this is a very trivial proof because this example is very trivial for the sake of simplicity. But yeah, later on, we'll definitely see more complicated examples for which this is actually useful to have. Let's look at another example. All right, we have our coin. So of course, the sample space is heads and tails. So the probability of heads is equal to the probability of tails, right? Because this is a fair coin. And they're both equal to 1/2 or 50%. So our indicator random variable, in this case, let's just say, for this example, we want the expected number of heads from one flip of a fair coin, right? Expected number of heads from one flip of fair coin. That's why I put event H into the indicator random variable. So since PR, which is the probability of heads, is 1/2, our lemma says the expected value of heads is equal to 1/2. Again, very trivial, simple example. I think it's like, you're like, yeah, obviously, you know, it's just a coin flip, right? It's just 50%. But this is just to show, later on we can build on this and have more fun, more complicated examples. All right, now let's apply this analysis to our recruiting problem. All right, so in this case, you know, we don't know what order the village is sending us the candidates. So we can make the assumption that everyone is in random order. So we're going to say X is the random variable for the number of acceptances or the number of times that you hire or accept or like take on this new disciple. Our indicator variable will just be like this, x1, x2, x of n, where xi is equal to the event that candidate I is accepted. So basically we're going to be looping through all the candidates. So given this, what is the probability that candidate I is accepted, right? Let's just say like we have loop going on. So my initial guess, kind of like my instinct, is to say, well, it's probably just 1 of n, because, right, we have n people, so like, you know, kind of like my gut feeling, my common sense was like, let's just say 1 over n, right? This is actually false. See, 1 of n is a probability that you keep the job, right? You stay on as the martial arts master's disciple. However, Remember, our random variable here is the number of acceptances. So the number of acceptances just means you have to be the best so far. You have to beat everybody before you. In that case, right, how many people were there before you? There was I people before you. You just have to be someone who can beat those I people. You just have to win over those I people that already came before you. All right, now let's compute the expected value. So remember, this expected value is just all of these guys added together. So to write this in a more mathematical way, we can say, all right, we can use sigma notation. Right? And now we can just perform some math. And after we substitute it in from our answer here, right, we get this. And lastly, what is this? This is actually called the harmonic series. Harmonic series, yay! So we end up with n plus this as our final answer for expected value. Okay, so big issue here. Remember what we said, right? We said, okay, we're going to assume that everybody is in random order. We're going to assume that they're just coming, the village is sending just them one at a time, random order. But we can't actually make that assumption because, again, we don't know if the villagers may be sending them in high order, in strength order, in age order. We have no idea. So we want to play it safe. And to play it safe, what we can do is we can manually shuffle them. Or, we can manually perform a random permutation. And this is just quite simple. You just loop through it like this, and you perform some swaps, right? So we're just looping through all the candidates, all the elements, and we're going to swap the current element with some random element. After we take the random number and put it as the index, we're just going to swap it. So if we do this, we can guarantee that we're actually randomly choosing a candidate.